Alright, so today we're looking at Module 8, Inquiry Question 1, which is the origins of the elements. And basically what this inquiry question is looking into is how do we get the elements of the periodic table, where did they come from? So the way we're going to start is we're going to look at a thing called nucleosynthesis reactions in main sequence and post-main sequence stars. The main focus will be looking into a thing called proton-proton chain and the carbon-nitrogen-oxygen cycle. So let's have a look. So obviously, as you can see, that's your textbook references if you need, and what we're looking into. So investigate the various types of nucleosynthesis reactions in stars. The main objective of this main question of this lesson is obviously, can you explain the process and write the relevant radioactive equations? So let's have a look at the life cycle of different types of stars. Now our star, our sun, it's a relatively small star in comparison to other stars in the universe. What we call is a low mass medium star. When the star runs out, or when our sun runs out of fuel, it will become a red giant. So it will cause this great expansion. So it'll make it expand out like so in all different directions. And it'll become a red giant, and then it'll become a white dwarf at the end. So that's what we're seeing. For the bigger stars, like a blue supergiant, they have the potential to become supernova and then also become a black hole. So as you would know, a black hole is an area or a area of space where the gravity is so strong it pulls in all the light in the surrounding areas. To represent the life cycle of the star, we can actually also use these diagrams here called the Hertzsprung-Russell diagram. The main function, as you can see, we have a thing called luminosity. You can think of luminosity as the intensity of the star. So how bright is the star? How many photons of light is it ejecting out? And then we also compare it in terms of temperature. Now this is in Kelvin, and we do it in an interesting different type of scale. We actually start with the highest value possible to the lowest value in terms of temperature, and then obviously in terms of luminosity we just increase upwards there. You can see that we have our sort of 1 point in terms of magnitude. That's kind of almost separating our big mass stars to the low mass stars. The stars that have a low mass will tend to have a value in the negative powers in terms of luminosity. The really big stars would have a positive power in terms of luminosity. There is a reason why we do that. We can explore that later when we talk about absolute magnitude. So there's that. Now if we're looking at the actual sequence, this thing here is called the main sequence. Okay, so the main sequence is showing the star in its current life form, like our sun right now, where it is producing fuel, it is producing energy to heat up the universe, to light up the universe. Our sun is around this particular range here. Very, very, as you can see, it is relatively low in temperature, very low in temperature, and in terms of mass, it's also a lot smaller. Now what happens is the sun, when it dies, it will expand and become a giant. When it becomes a giant, it goes here. You can see what actually happens is the temperature hasn't actually changed, but the intensity, overall intensity of light produced by the particular star will get higher. Okay? Once that's done, the supergiant will then become a dwarf. In the diagram we showed before, that is a white dwarf. Okay, so that's what we're looking into here. If we're looking at the supergiants, so the ones that are really massive, they go from the main sequence and become supergiants. Obviously from there, some of them might become the dwarfs as well, depending on the mass, but they will potentially turn into supernova and thereafter. You can see their intensities also, majority gets higher, but their temperatures do decrease a little bit as they expand away. Now, these two spots, this is what we call the post main sequence. So the life cycle of the star, where it begins to start dying, causes the great expansion to occur. So let's just go through. The main sequence stars are the stable period of their life cycle, so they're like our sun, where it's still producing fuel. Post-main sequence is when most of the fuel has been consumed and they are progressing in becoming a supergiant or a red giant, or red supergiant or supergiant. Okay, so that gives you a little context of what the two types of stars are. Next, we're going to look at a thing called nucleosynthesis. Okay, now nucleosynthesis is the formation of a new atomic nuclei. When we say nuclei, it's pretty much just plural for nucleus. So we're saying a nucleosynthesis reaction is when a new nucleus of a set element or set atom is formed. And this is quite fundamental because this is how we form elements of the periodic table. We're not talking about the electrons because the electrons aren't quite involved in this procedure. We're purely looking at the nucleus here. Okay, so if you actually have a look at this diagram, it actually illustrates quite nicely how each element of the periodic table is actually formed. Now, obviously, the ones down here, 95 onwards, as you can see, that falls under the human synthesis. So we have actually developed the technology where we can make artificial atoms. Okay, all those though tend to be quite radioactive, so they're not very stable. They actually break down very quickly. If we have a look, we have hydrogen, we have helium, and we also have a little bit of lithium, and that you can see with the lithium we created there, that's partly to do with the Big Bang fusion. So when we talk about Big Bang fusion, we're talking about the great expansion and then how energy was converted into mass, and then how that mass began from simple elementary elements to make protons and neutrons. They combine to make the first few elements of the periodic table. You can also see beryllium is made from cosmic ray fission, so separating of the atom. You have boron, and then when a low mass star begins to die out, you can see there's a bit of formation of carbon, nitrogen, and so on. Okay, so there's that. What we also know is, with our understanding, most of the energy, expansion, and the pressure of creating a particular element, low mass stars or first generation stars can only generate up to iron. To have all these other elements of the periodic table, you do need the star to re-emerge again, have a second life, you could even say, and create newer elements. So that's the set limit there that we know of. Okay, so to go with explaining how stars generate energy and create the different elements, I just want to point out one fact here. So a star is initially composed of a hydrogen nuclei, which is, the nucleus of a hydrogen. Now, if you know your chemistry, a hydrogen nuclei is the same thing as saying one proton. Okay, we can represent it like that. Remember, top number here is the atomic mass, mass number, and then the number down here is the atomic number there. The main objective with these fusion reactions is to create a helium nucleus. Okay? So in order to synthesize a helium nucleus, 4 hydrogen nuclei undergo fusion. 2 protons will end up becoming neutrons. However, the probability of having 4 hydrogens, each colliding with each other to make a helium atom, is very low. Okay? So our objective is to get from 4 of these to these, but the science says the probability is very low for them to just get to that straight away, and the energy required to make them collide correctly is also very difficult. So the barriers are too high for this to go to this. So we actually have different methods, or the universe have created different methods in which that can be done. And we note this as the proton-proton chain, and then we also note this as the carbon-nitrogen cycle. This is a quick word of ideas. This is obviously nuclear fusion. Both of these we're talking about, and some context it has a bit of nuclear fission. But both of these follow the same idea. So both of them, the net change, so both of them will have 4 hydrogen nuclei, and it will end up becoming a helium nuclei. There are some other particles that are produced, or some other radiations produced, but that's the actual thing. So both of them do it, but they do it in different ways to each other. Okay, so the first one we have is the proton-proton chain. Now most low mass stars will go through the proton-proton chain, and like I said, fusion between 2 protons initially, and then it will form helium, helium-4, and also some energy will be released. So the idea is very simple. Starting point is 2 protons colliding, then you get hydrogen 2, and it gives you 2 products. That's actually the first step you see in this little clip here. So let's kind of have a look. This is actually the set diagram to show where we start. So the starting point here. So this is our starting point, and this is our end point. If we actually look at our starting point, we have 1, 2, 3, 4 hydrogens, and we do get 1 helium at the end. Okay? So as you can see, there's actually 1 collision here, 2 collisions here, 3 collisions here. So there's 3 steps involved in producing the hydrogen into helium. So we're going to look through each one and see what this diagram is showing us. Okay? So the first step, and this step occurs twice, is you have 2 protons that would collide, and that would create hydrogen 2, deuterium. It will create a positron, a elementary particle that's not known to you right now, but we will talk about later on, called the neutrino. You can consider that as radiation as well, energy. And it also emits 1.44 mega electron volts of energy. And like I said, this reaction actually occurs twice. So whilst this equation is showing 1 reaction, you can always say that there's actually 2 involved. So that's what we mean by it's occurring twice. What happens afterwards is the deuterium, so hydrogen 2, is going to then collide and combine itself with a proton. They're going to collide. That's going to create a helium nuclei, and it's also going to create gamma rays. Okay, and obviously, as you know, gamma rays are just electromagnetic waves. It's also just energy there. That produces 5.49 mega electron volts of energy, and at the same time, also, it occurs twice, as you would have seen in the image prior before we started this conversation. The next one we have is then the helium-3. So now you have two helium-3s from the two reactions that you have, and the two helium-3s are going to collide with each other. It's going to produce a helium nuclei, and it produces two protons. So these two protons can now be used for step 1 or step 2. So it can collide together to make hydrogen 2, or it could collide with a hydrogen 2 to make helium 3. Okay? This last step only occurs once. So unlike the first two steps which occurs twice, this only occurs once, and it produces 12.9 mega electron volts of energy. Okay? So that's what we have. If we want to put like a general net equation, so what's actually happened overall, this is what we see. Okay? You can see that the 4 hydrogens have collided to make helium. We've produced 2 protons in the process, so they've been ejected out. The reason how they've been ejected out is obviously because we've given off the charges, okay? And some of those decay has decayed into a neutron instead, inside the helium here. We have released 2 neutrinos and 2 gamma rays. If we actually look at the process of how long it takes for this to occur, we can see this collision has a collision time frame of 10 to the power 9 years, so it actually takes ages. Then the second step, about 1 second, and then the next one, 10 to the power 6 seconds. In terms of why they differ in so much, I assume it's to do with the properties in charges and collision energy requirements. Okay, so let's just do a quick summary of the 3 steps of the proton chain. First step is you have 2 hydrogen isotopes, hydrogen 1 isotopes, fuse to produce a hydrogen 2 proton or positron, neutrino, and then 1.44 mega electron volts of energy. Remember, step 1 occurs twice. Step 2, we're going to use the hydrogen 2, and we're going to collide it with another hydrogen 1, or they're going to collide, we don't collide it, and that's going to produce helium 3 and gamma radiation. Again, this step also occurs twice. And then the last one, the 2 helium 3s from the second reaction are going to combine together to make helium 4. That's going to produce 2 protons, and it's going to release a combined energy amount. Ooh, I didn't have that number there, but as you remember, it was about 12 mega electron volts. Okay, this step only occurs once. Alright, so what you can see here, we talked about, we have the main sequence star. It is, once it runs out of energy, it's going to become what we know as the post-main sequence. It's going to start expanding in all directions. The reason why it starts expanding is obviously the fuel source is pushing outwards. So that's what we have here. And then it eventually collapses on itself as it's increasing the amount of content inside, and then just weight of gravity, the gravitational force pulls it back in. Okay, this is actually one of the processes. We actually know that there is another way of doing the proton chain. This is just another alternative, but the ones that we talked about before is the most known one that we know of. Okay, so the diagram, we're looking at the proton chain, what each component is on this chain. We know that N is just the neutron, P is proton, the light that's coming out, then obviously that is gamma rays. We have this sign here, I do believe that is the proton. And this final one here, I would presume that is our neutrino. So there's that. Alright, if we actually have a comparison look of the proton chain and the CON or CNO cycle, you can see there's actually a time period where one is more favored than the other. So for the proton chain to occur, we need about 1.1 10 to the power 6, so about 1 million Kelvin inside the core of the sun for the proton chain to occur. So it needs to be that hot before the proton chain process begins. Our sun is at this point here in its core. Remember, the core temperature is different from the surface temperature, and as you can see, in our sun, we do have the carbon, nitrogen, oxygen cycle occurring, but not as much as the proton chain. That will occur once we've passed about 10 million Kelvin, and as you can see, as the core temperature gets warmer or higher, the carbon, nitrogen, oxygen cycle becomes more productive. Obviously, what that would imply is the bigger stars, the more massive stars, will tend to have a higher rate of doing the CNO cycle than the proton-proton chain. Okay, so let's have a look here at the cycle, the CNO cycle. You can see that what's actually happening here, you can see all the different elements or all the different nuclei. Now, one of the things with this, besides the fact that it's dominated in big main sequence stars, is the carbon, nitrogen, and oxygen that you see in this video here. They are just a acting catalyst, so they allow for the procedure to occur, but they're never actually involved in the overall process. Well, they're not involved, they won't change, but they help cause the change that we see here to get those 4 hydrogen nuclei and become helium at the end, or helium-4. It is temperature sensitive, so don't forget that, okay? So, the carbon-nitrogen cycle, carbon-12 is the first one we have here. It's an acting catalyst to cause reaction. So the carbon-12 is going to collide with one proton. That's going to make it into nitrogen-13. In that process, gamma rays will be produced. This nitrogen-13 is a highly radioactive isotope, so it's going to go through nuclear fission. It's going to break itself apart. It's going to release a positron, and it's going to produce a neutrino. That's going to make it go back into carbon-13 because it's lost a charge, so our charge number goes down. Carbon-13 then collides with another proton. That's going to release a gamma radiation. That's going to make it into nitrogen-14. Now that's pretty stable, so it's not going to go through nuclear fission, but you can then have another hydrogen collide with the nitrogen-14. That's going to eject more radiation, makes it into oxygen-15. Now that is radioactive or unstable, so this nucleus is going to try and break away from each other. So to keep it stable, we release a positron, okay, and then we also release a neutrino, and then we have nitrogen-15, which is stable, collides with the 4th proton to make helium-4, and we get our carbon-12 back again. So it's quite a rounded way here, but as you can see, we've kept having the same nucleus. It's just an intermediate stage. It's used to allow for the release of energy, and it's allowed us at the final stage to release helium-4. Okay, so there's that. So if we actually have a look at the main procedures, the first step is the carbon-12 collision. The second step is the nitrogen-13 fission, so breaking itself apart. Next step is the carbon-13 fusion, again, nitrogen-14 fusion, oxygen-15 fission, and then nitrogen-15 fusion. Okay, so that's the actual process. You can see these are the actual values of energy that's being released. Now, you don't really need to remember these energy values. You probably don't need to remember the actual process in terms of directly how to rewrite all the formulas, but they might ask you in the HSC, if you have this reacting to make nitrogen-13, what was colliding with, carbon-12? Oh, that should be carbon-12. I don't know why they had that there. So why is that? So filling it out that way. So they might have one of these blank, and they might want you to fill out to see what the nuclei used was exactly. And they'll probably ask you in terms of the energy production overall, how much energy was produced in the reaction, those kind of stuff. Okay, so that's what we mean by the post-main sequence stars. You can actually see that with sufficient mass, a star's gravitational force will be able to sustain the density necessary for helium to fuse into heavier elements. So that's where we get different elements of the periodic table form. Usually it becomes carbon and oxygen. Very massive stars are able to continue fusing elements all the way to form iron. This is an exothermic reaction, hence why it produces so much energy. The more dense the element, the closer it is to the center core. And it will produce an outward force of radiation as it's producing, preventing the star from collapsing under its own gravity. So that's kind of how the star keeps moving outwards and not collapse until much later. Okay, so some questions here, fusion of the main sequence stars, 2 different types of fusion possible, outline how it works, and then what determines these processes. So there's that. A couple of questions I do want you to have a look at is some past paper questions on the carbon-nitrogen cycle, and also that, or just this one here. Okay, so that kind of sums up what we were talking about today with the nucleosynthesis reactions in stars. We focused on the proton-proton chain, and we also looked at the carbon-nitrogen cycle. Remember, as we said, at the end of the day, it's getting 4 protons to make the 1 helium nuclei. Do remember though, there are some slight subtle differences besides the procedure. The protons do give off a different amount of the overall particles than the carbon-nitrogen cycle. From memory, the carbon-nitrogen cycle gives off 4 gamma rays, while as the proton-proton chain only gives off 2. So that's the main difference between the two there, okay? So that ends the lesson for today. I hope you enjoyed it. I hope it was informative. And I'm going to keep going with the next video, which will be about, if I recall, how mass energy equivalence works with the production of energy, and also what we're going to look into is, again, back to spectra of stars. Okay, so until then, catch you later. Hopefully this was helpful.